Now, data center efficiency is measured in power usage effectiveness, or PUE. So this is a ratio that describes how much computing energy is used in computing equipment versus everything else in the data center, like cooling, heating, and so forth. The industry average is around 1.56 and hasn't improved much since 2020, according to the Uptime Institute survey in 2024. Now, that being said, there's a lot of drivers for the AI facilities to get this better PUE to be more efficient in their energy usage. So, when we're talking about data center load profiles, in a traditional data center or cloud data center, these are typically high availability data centers that have high uptime requirements, so the load profile is pretty constant. But for data centers focused on AI training, the profile is generally rather variable. So as you're training the model, the software is taking that AI model, training it, feeding it inputs, and then grading it based on its output. We have software programs that are driving power demand, and this power demand can change due to new code, new firmwares, compiler updates, you know. So this is something, how do you model changes in software driving power demand in your forecast? That's a difficult thing to do. And for data centers that are focused on AI inference, which is the using of the model compared to training, the load profile is typically a little less variable than a training model, but it's probably a bit more variable than your traditional data center. And so this is an image from Google, showing a 15 megawatt peak to peak variation in their load while training an AI model. So inside the data center, you really need to understand what's in there to figure out how do you model this and account for it in your grid. So there's a lot of different configurations. What we put here is just a sample. Mains power, you go to your uninterruptible power supply, and then to your server power supply, your rack power distribution unit, and then to your compute. Now you can have AC versus DC server buses, centralized versus distributed UPSs, and power distribution. But primarily, it's the rectifier or UPS that we need to be concerned with, or the power supply if there's no UPS. So these are typically designed according to the ITIC curve, which specify will the equipment trip or not trip. And when we're talking about voltage ride through, we need to look at what these ITIC curves are and see, is the equipment designed differently? Because while there is the ITIC curve, folks may design their equipment a bit differently. And to get better ride-through performance, we need bigger onboard capacitors on the power supplies, UPSs, and rectifiers, which is more expensive. And so therefore there's a cost and an engineering trade-off. Now for cryptocurrency mining, um, I'm sure most of y'all are aware of Bitcoin, so that's one of the most famous cryptocurrency. So with cryptocurrency mining, the computers are trying to solve mathematical problems to unlock new coins. And really, the things I want to focus on is crypto mining is a pure arbitrage play. So miners are taking energy, electricity, and basically turning it into money. As such, they're really price responsive, and as long as the price is advantageous, there's little demand variability. They want to be producing to make money. And then the miners will typically run specialized ASIC miners, which are designed to UL specs, not IEEE. So you can run these at home or in a server farm, and they typically have no special write-through capabilities. There's no backup generation or UPSs on these sites. So where will data centers go? This is a great diagram from NREL. Um, I'll let you all peruse this at your own leisure, created by Billy Roberts. But this is a map showing transmission lines and fiber optic lines. Uh, so you'll start to notice Northern Virginia on the East Coast, there's a lot of data centers, there's a lot of power availability, and there's a lot of fiber availability. In Texas, you'll see major fiber trunks where data centers are going in. So if you're wondering where they want to look, take a look at this map. You'll probably be able to get a good sense of, oh, why is my data center going there? So we're going to talk a little bit about some of the large load events that we've seen across the system now. Across the world, there have been several. So there's a Dominion event where there was 2 one 1500 and an 1800 megawatt event where data centers tripped, and there's also been data center oscillation events. In AEP, there's been 2 faults where data centers have tripped. In ERCOT, we've had multiple trips of cryptocurrency miners and a 1500 megawatt load reduction event, and then a compute oscillation event. And then in EarGrid, they've had multiple events, with the largest having 321 megawatts in data center demand reduction. So we'll talk a little bit about these in more depth. So ERCOT, we're seeing a lot of events where load is not riding through too well. This behavior is not captured in the existing models, so there might be protection systems or other facility models that are not included in our dynamic models. And then single line to ground faults, we're seeing those is causing significant reductions for positive sequence voltages, and they're the most common. However, the 3 line to ground fault will have an even bigger impact on the load. We've also seen an oscillation event. So in 2024, we saw 40 megawatt oscillation when a large load was above 300 megawatts. We eventually saw a 23 hertz oscillation with 50 megawatts peak to peak magnitude, and the root cause resolved firmware. So again, this is computer software driving load, and that's a thing you have to wrap your mind around. How do you account for that in your model? So this oscillation was subsynchronous and could have damaged nearby generation, and we really needed high resolution measurements that we did not have. Off the bat, SCADA was not fast enough to catch this. So in Dominion, 230 kV fault led to about 1,500 megawatts of voltage sensitive load. This is in 2024. NERC published a event report on this, so I won't go into all of this, but really the thing to note is most of this load reduction came after the 3rd voltage depression, which was the 3rd automatic reclosing attempt. So after the 3rd reclosing attempt, a lot of load tripped off. So most data centers use a 3 strikes rule before switching to backup power, and that's something you need to think about, and that's something we as an industry also need to talk a bit more about, figure out how are our protection system settings impacting load, and can that cause load to drop off. In AP 2025, they had 2 normally cleared 138 kV phase to ground faults. They had data centers and crypto miners in the area. Some of them rode through, some of them did not. And really, again, this is centered around that 3 strikes rule. You have high speed reclosing with normally 3 attempts. So after that 3rd high speed reclosing attempt, the data centers tripped off in this event. So here we can see some of the oscillography, and you can see that this is an 80 megawatt data center that trips after the 2nd reclosing event. So this was presented at NERC's LLTF if you want to follow up for more information. And then in your grid, there's been 3 transmission faults that caused the transient voltage dip, the largest of which resulted in a 321 megawatt demand reduction. And again, this was triggered by data centers transferring load to the UPS due to protection system settings. This did cause some frequency spike, and the reconnection of load also posed a challenge to system operators. So again, we're seeing voltage protection settings and UPS and device protection settings impacting the load on the transmission system. So ultimately, these large loads are an emerging reliability risk. While we haven't had any blackouts or, huge negative impacts of these yet. Each as we go forward and forward, more and lower load is tripping. So there's no regulations on registration requirements. There's very few operational rules or good models. So we have these loads that are unmodeled, unsimulated, and unpredicted, which is exacerbating the risk of blackouts. We used to watch Terminator, and we saw Skynet taking over the world, threatening our power grid. Well, you know what? The risk is here now. We don't have to wait for Skynet. So we need folks to work together to make sure that the grid is supporting the data centers and loads, and that their behavior is also supporting the reliability of the grid. So we have a couple efforts that are ongoing across the industry. We have the NERC Large Load Task Force, which is focused on the reliability of bulk power system. We're publishing 2 white papers and a reliability guideline. This may need to may lead to new standards, but they are limited to looking at standards and practices. They can't propose specific technologies, and the participation from the load owners and developers themselves, is not as high. The Energy Systems Integration Group Task Force is looking at a more holistic view. They are also producing a white paper, but we have a lot of participation there from load developers, and we can also look at specific engineering solutions and then try to find things that are mutually beneficial for both the load owners and the grid operators. Because, a load owner may just tell you, if you try to impose right-through standards, my UPS just cannot do that physically, so we need to come up with a new solution. And then ERCOT has a large load working group as well, focused on the reliability of the ERCOT system, and this is recommending policies and procedures to facilitate the load integration into the ERCOT system. They're covering both technical and market issues, and then producing work on how do we integrate these. So moving forward, we need to look at these loads and really understand how they operate, characterize them, and develop good models of them, both electrically and behaviorally. So in response to transient disturbances and steady state conditions, and then behaviorally, what do their load profiles look like? So we need to understand that three strikes setting on between interaction between the power transmission system protection and these power electronic loads. And so we really need to build more partnerships between grid operators and load owners and developers, which is underway in these various task forces. So the industry needs to keep doing that. However, just keep in mind this will evolve into requirements and changes that grid operators will need to implement. And certain loads may need to become registered entities and have regulations and performance requirements applied. We're working through that through these industry task force and working groups. And so this is really a new challenge for the industry. And, similar to IBR integration, we've had decades of the grid being relatively static, and that's changing now. So, but we need to move fast because the longer we wait, the greater the risk is. And now I will hand it over to Evan Mickelson.
Really nice presentation, Eric. All right. I'll get started immediately here. So I'm Evan Mickelson. Thank you so much for being here, and thank you for having me. I'm going to be talking about large electrical loads and their impact on the grid reliability. I'm going to walk through some key findings from NERC's recent work and kind of highlight the other things that we're working on and some of the risks that we're seeing in the grid right now. So first, this is from NERC's 2024 LTRA, and they were really looking at what are the primary demand drivers by the different NERC assessment areas. You can see a common one here is data centers and industrial loads, among other things. So, it's not just data centers, it's not just crypto. There's a lot of different large loads growing across the US, and they each pose kind of unique challenges. So some of the challenges that we're seeing already, as Eric mentioned, there's some really big pockets of large loads in the Eastern Interconnection and in Texas. We saw particular events where normally cleared faults resulted in large losses or transfers of load to their backup generation. And then additionally in ERCOT, due to various faults with three-phase or single-phase, we see varying amounts of large load loss. And so there's already large events happening, and it's reminiscent of the IBR, as Eric said. We had a lot of loss events with IBRs, and eventually we were able to analyze each of those and make new determinations of best practices, and I think that's what we're looking to do here with these. So this specific event, we released a incident review and tried to analyze what exactly happened and provide that to the industry as guidance. One big thing we saw here was that it wasn't just a single 1,500 megawatt load, it was 60 different load points across 25 different substations. So a lot of these were electrically close, and the fault was seen by all of them, and they were tripping offline. So it kind of begs the question, do we need better models for these? And would we need to modify any standards for large loads and potentially look into registration for those? So I'll kind of rewind a little bit more and go back to August 2024. That was when NERC formed the Large Loads Task Force with the primary goal of understanding the reliability impacts of these emerging large loads, specifically to the bulk power system. They identified a few types like data centers and hydrogen fuel plants, and also other emerging industrial loads. And we are using the framework to address known and emerging reliability and security risks. And that process pretty much looks like this. First, identify, validate, and prioritize the risks from large loads. Then do some gap analysis and figure out, are some of these things already mitigated with our existing processes, or are some things unmitigated currently and we need to develop new processes or standards for it. The final piece, the reliability guideline that's slated to come out sometime next year, is, okay, now that we've found the gaps in existing practices and standards, what specific changes to processes like an interconnection in modeling can we recommend to mitigate the risk from large loads? So this is kind of a visual view of what the papers look like and what they're aiming to do. White paper 1 really aims to say, all right, these are the categories of large loads, and these are the common characteristics. Based off of those characteristics, we see risks to the BPS in, for example, frequency stability. And so that's pretty much where white paper 1 stops, and white paper 2 picks it up and says, all right, for frequency stability or all the other risks, where are the current gaps in practices, requirements, and of course, NERC reliability standards? Through that, they were identified specific gaps in the risks to the bulk power system. And so I'll start talking about some of those characteristics and risks from white paper 1. And then I'll start talking about how we plan to accomplish the rest of the white papers and reliability guidelines. So this is all material from white paper 1, which is slated to release in July this year. And these were the initial categories of large loads that we determined, and is computational load, or compute load, as is common in the industry. Industrial load, all the different types of industrial loads, and then of course hydrogen production facilities that use electricity as the primary conversion method. So some of the characteristics of these large loads, and this isn't applicable to all of them, but for things like data centers, they have really fast interconnection timelines. And in some cases, it's even faster than the fastest to build generation. And of course, transmission lines are known to take a very long time, maybe 5 to 15 years, depending on the exact project or where it is. And so this of course, leads to the risk of data centers being built faster than we can build the other things that are needed to support them. Another characteristic that we're looking at is just the general demand profile. As Eric mentioned, with the traditional data centers, you might see something more like this middle one, where it's very static, and it may change a little bit, but it's generally the same over time. And maybe the one up top isn't something that we're seeing on the grid right now, but this bottom one is certainly something we're seeing with AI training loads. And they'll be training and then decrease their power dramatically to do a checkpoint, and then they increase again to a large power demand in order to continue their training. So this is one of the characteristics we're seeing across the different types of data centers. Another thing is ramp rate. So this is sourced from EdgeTune Power. This is specifically an AI training data center, and this shows a few of the fast ramps up and down. You can see they started a training run somewhere here around the 300-second or so mark, and they very rapidly ramped up, as we're seeing a ramp of about 0.7 per unit per second. This is a 50 megawatt data center block. And of course, the most rapid ramp we saw is here at the second ramp up, and it's 1.9 per unit per second. So very, very rapid fluctuations in demand. And of course, this is a 50 megawatt facility, and it's a lot smaller, but you can imagine what that might look like if you have a really large facility or a lot of different facilities all ramping. Another characteristic we're looking into is voltage sensitivity. So a lot of the data center equipment is very sensitive to low voltages, and they might trip in order to protect their IT equipment as low as 0.6 per unit for just 1 or 2 cycles. So this is certainly something where the data center industry and the utility industry need to collaborate to figure out what are the limits there and when can we expect them to trip. And then this is the last challenge I'll cover is the current existing standard library models may not fully uncover the risks associated with these loads. And so there are some really great models that people are using, like the EV model, in order to kind of approximate the large load behavior. And in some situations that works really well. So I'm not saying that all large loads cannot be simulated right now with existing dynamic models, but there's certainly challenges in representing specific modes of failure. And so that's another characteristic that we're seeing. So this is just a draft. I want to really emphasize draft, a draft prioritization of the risks that we're seeing based off of those characteristics. And so we've tried to bucket them in terms of high, medium, and low. And some of these will be changing in the final draft. I know for a fact that cybersecurity is probably going to be moving up a bit because I think the cybersecurity risks are highly related to the stability risks, which of course we've marked as a high priority. So I'll just cover the high priority risks. We're looking at resource adequacy as a major risk. Like I mentioned, data centers can come online much more rapidly than generation. And so we see that as a very high risk at this point. As of course I mentioned, the rapid ramping, which can cause great challenges for balancing and reserves. And so we're looking at that as a high priority item to address and mitigate. Additionally, we see some issues with the existing UFLS programs. You would do the assessment about every 5 years, at least as required by the standard PRC6-5. And of course, we've already covered that certain large loads can connect in under 2 years. And last thing, and this is actually the same graph that Eric showed, but that stability is an issue, and it's not just oscillations, it's also voltage stability. Ride through is very related to those issues. And we're also seeing angular stability as an issue. So all of these pose risks to the bulk power system and could result in cascading outages, islanding, separation. So we're looking at these as very, very high priority risks to address. So once again, I want to remind people that this is draft and the final version will come out in July. But these are some of the recommendations that we've put out so far in draft. And I can say most of these will stay the same, but some will be changed. First, we just want to recommend that we go ahead with the gap identification and risk mitigation, that those would be really critical steps in mitigating the risk from these large loads. Additionally, we want to recommend to certain reliability and security technical committee working groups to like the load modeling working group, that we want them to definitely continue work on model development and refinement for large loads. We also want to work with our system protection and control working group to assess the potential protection system impacts, and working with the data centers to figure out what does their protection look like? What does the utility protection system look like? And do we need to change things on either side in order to make sure that we see tripping as intended and is as is planned, not something that we're surprised by. And then we also want to investigate further risk to resource adequacy. We think that that could be a really big issue. Of course, it's high priority. So, and we didn't have we didn't go fully in depth in the paper. And so we think that it would be great for an RSTC group with subject matter experts and resource adequacy to really fully explore that. And the last thing is a recommendation to utilities and all the audience of the paper is that they should be collecting the data necessary to understand these risks associated with the large load. So anything that I've mentioned on the other slides as far as risks from the high priority, medium, or low, that all of those risks need to be understood, and that collecting data is one of the best ways to address those risks or to understand the risks. So I've already talked about white papers 1 and 2 and how I plan to identify the risk and figure out where the gaps are. And the reliability guideline is the one that we're currently working on. And it really aims to figure out, okay, how can we mitigate those risks with specific changes to our processes through data collection, modeling, coordination efforts, analysis, real-time monitoring, and event analysis. So we're not going to recommend any technical solutions as far as equipment to install at the data center or other large load. We want to recommend that if a certain study needs to be performed or a certain event analysis needs to be performed to mitigate any risks to the bulk power supply, that those are implemented as best as possible. So I think that's my time here. I came in a little under 15 minutes. So yeah, ready to move on.
Thank you, Evan. Thank you very much. We can now jump into the more of a conversational section. Let me just quickly share my screen to just because we received one question related to the slides, and I think now you see a website. This is the CIGRE US National Committee website. Here you will have access in a few days of the recording of the webinar, but also the slides. So just for everyone to that wanna get them, just maybe either do a screenshot of this website, or also I think I reply already in the QR in the question section with the link, a link to this website. And now opening the floor for the conversation section. We have been speaking about the white papers, right? During this Evan's presentation. This is one of the ones that Evan referred to. One of the incidents that happened in the eastern coast, and I would like to. I mean, right now you can both reply, but my first question will be especially for you, Evan. After this event, has there been any fundamental shift in the collaboration between NERC and large loads operators after seeing what could have happened for this event?
Yeah, I don't know if it was this event specifically that triggered it, or kind of just other general industry talks, but we definitely see that large loads are getting involved in the large loads task force, and we definitely work with certain loads, but some are not as willing to be able to share all of the information that we might need. So definitely seeing an increase in collaboration.
Mm-hmm. And you, Eric, have you had any fundamental change from, I mean, maybe the work that things are like the conversations that you have, or the work, or maybe even like new working groups that you have created on to kind of address this?
Yeah, look, we've turned our large flexible load task force into a large load working group, recognizing that this work is going to continue. We are seeing greater participation from load developers and owners, and then have communications with them. So I think it has been an increase, but as Evan said, not everybody is willing to share information. So we're doing the best we can with, the folks that are willing to work. And for everybody, out there, we do encourage you to get involved in these efforts, whether it's through eSig, ERCOT, NERC or any other means, that will help us tremendously and help ensure the reliability of power to your facilities as well.
Yeah. During your presentation, Eric, you touched a little bit on UPS or uninterrupted power supply systems. Is that something that, for example, is something that we could work on a little more and have a better understanding of that? Will that you having an understanding of that portion of that technology of these large load users, what kind of UPS they use? Will that help you to kind
It
of?
would help to get good dynamic models and EMT models of these loads now, but something to be aware of is that there's a lot of different versions of it. Not everybody uses UPSs on their servers, depending on the application. Some people, a lot of the big entities design their own equipment, so while you can purchase some off the shelf, other people may have custom designed equipment. So there's a lot of what's applicable in one data center may not be applicable in the other. That said, there's, only a handful of standardized server designs for the most part, and a lot of the information that is public you can find on the Open Compute project, which has a lot of the specifications out there for rack and power supplies. But it is something that engineers in general in the power industry, if you want to work on modeling these loads, you need to understand how the loads work.
Yeah, thank you. Yeah, and for our listeners, I recommend reading this publication because it explains quite a bit of the background of what we are talking about right here, and how these uninterrupted power systems may make a funny interaction with the grid. So now that you were touching on, like who designs what and who makes what, and how that information flows, from your point of view, and this is also for both of you, which entities should be involved and work together? Is there like the users, the manufacturers, the companies in charge of the installation of these power systems for the data centers, for example?
Yeah, I think you need to have multiple people involved at different points. So if you're building a data center, you may not fully know what the equipment inside of it does. You may need to talk to your UPS manufacturer or server manufacturer. At the same time, they may not know why you asked them for that detail. And then once the facility is commissioned and going on through its life, that's an ongoing collaboration between the owners and the equipment manufacturer. And if you have somebody manufacturing their own custom designs, then you need to be working with them as well. So I would say you need to work with the equipment manufacturers, you need to work with the site developers because they're the ones that'll tell you which equipment's going in there, and then the owners, because they'll tell you what is in there once it's operational. And then once it's operational, what is actually happening in the facility. If you're training AI models, they may be able to say, hey, we know that we're training this model, we're about to spike power demand. But they also may not know, because if you're running a data center and Andres and I'm running my load on your data center, you don't know what I'm running. You don't know if my compute is suddenly going to shut off. So it becomes a very difficult problem where nobody really has access to that information. So how do we work through that is something we all need to think about.
That's good. Moving on, maybe to maybe a little more technical question for you guys. So for mitigation methods, for again bringing stability for these large loads, what will be like a good mitigation method for large loads tripping or disconnecting suddenly? Any ideas?
Yeah, I would say definitely study. This seems to be one of the best things we can recommend, especially from NERC side, is that, I think, and this will come out in the reliability guideline, is that the best way to make sure that you're not going to have some sort of cascading effect or large effect on the bulk power system is to make sure that you study this with as much detail as is available at the time that you have it. And so we recognize that maybe 3 years out, you don't have a firm dynamic model for the load, but with the best information that you have available, you should be studying it. And so I would say that's definitely the mitigations that NERC is recommending at this time.
And I can probably I'll echo what Evan said, study, study, study. But once you've studied and it still shows a trip, what do you do? And there's a couple, you could do hardware solutions, technological solutions, and everything I'm about to say is up to the owner and developers in some respect. But from onboard solutions of bigger capacitor banks on UPSs and power supplies could help you ride through, but that costs more money. Batteries, energy storage resources at the plant could help you ride through and inject power, right? So there are mitigation methods, but you have to face the reality of what is the hardware designed to, and there's already a very large installed base of this equipment out there. We can't just go and rip out every single power supply that's ever been built. That's not going to happen. So I think we need to study it, but we also need to be working on this proactively together. We're not going to come up. I'm not an expert in data center design. We need those people that are experts in data center designs, for example, to be there helping us.
I see. And that was potentially one of my other questions. Who is missing from the conversation? So please, data centers experts, come to the conversation.
But I also want to remember this is a large load webinar, not a data center webinar, right? So
Yeah.
the same goes for those developing hydrogen facilities and other electrofuel facilities, those developing cryptocurrency miners, those developing new semiconductor plants that can also be very large, oil and gas, processing facilities, natural gas liquefaction trains, everything that is large, that's what we need to understand. So there's a lot of different types of demand and a lot of different types of expertise that we're going to need.
Yeah, thank you. Very interesting. And this is the last one I'm going to throw to you. I think we discussed this slightly during the last meeting. So how many gigawatts of load are manageable of your system to be disconnected? What is serious can be a trouble of large loads disconnecting suddenly?
I watched an ERCOT presentation last Friday. So I don't know if I'm kind of stealing this from Eric, but they did a fantastic study where they looked at the frequency stability limits and the voltage stability limits of a specific area of their system. And they tried to use like a low inertia case, something where there wasn't a lot of foot room, which is kind of a kind of new idea, is how much can your reserves regulate down. And they did find a specific number of megawatt limit. I would encourage you to go to the ERCOT LLWG, find the presentation. Yeah, they found a specific number. I think it was 2,000 megawatts for voltage stability in a specific area of their system, which is highly local. And then they found 2,600 megawatts as a frequency stability limit. So, and then there's a lot of different ways to look at it. So those are just two specific ways to look at limits. And so then they need to know who's going to trip, and are we going to be able to hit that 2,000 megawatt trip due to like the most severe fault. So yeah.
Interesting. I think we were discussing the other day also, it depends on the location, as you well said. So it's depending on where's that load, you may have more bandwidth to solve it. Yeah. All right. So yeah, from here, I think we are done with our time for the discussion section, and now we'll jump into the Q&A. Let me stop sharing my screen, and now we'll have Melvin. Are you still there? Do you wanna go ahead? Also, maybe with the questions. Can you?
Yeah, I think there was a couple of questions that we can talk about that I feel like that are really important. There was a question from Steve Singer. Has any EMS vendors being a part of the model development discussions? Yeah, this might be a question to you, Eric, or to Evan as well, with respect to the large load task force and other ones.
Also, not that I'm aware of. And something to keep in mind too, while we're talking about all these complexities in the steady state simulation, which is typically what your EMS is doing, a load is a load. Whether it's, 5 megawatts or 50 megawatts or 500 megawatts, it's a load, and I'm computing my static and voltage, static voltage and thermal violations. Now, when we talk a little bit more about, transient stability applications, online studies, maybe they need to be more involved, but that's where, as long as there's a common type of dynamic model that they can accept, it should be pretty well. We're not inventing new technologies sort of here and methods out of the box. We're just applying a lot of traditional power system analysis techniques to a new problem. They might be slightly different inputs, but the core methods of voltage stability, transient stability, your steady state analysis and short circuit are pretty much the same.
Thanks, Eric. Evan, do you want to take a swing at that, or?
No, I think I'll yeah, hold off for that one.
Okay, okay. I think so there's another question that's becoming a theme that everybody's talking about is what are the mitigation strategies? I remember when we were initially having that kickoff meeting in Austin, one of the mitigation strategies that was thought about was StatComs. As in, like, has the large load task force at any of the places that's NERC, ERCOT, or ESIG sort of got into a place where you can start talking about the actual mitigation strategies for some of these issues that we're seeing right now?
Yeah, I think there are multiple issues, so it depends on what you're trying to mitigate. eStatComs can be a technology that is something we're looking at in the ESIG Large Load Task Force, where we can look more at specific technologies. And then something that I say, to think about too is a lot of this we're talking about is fluctuations in on the data center side, AI training demand, right? There's sudden fluctuations that are causing problems. And there's some good work that's come out of Google where, fluctuations are not just a problem for the power system, they also wear out the equipment on the data center side faster too, and cause wear and tear on those devices. And that's not something data center owners want. So there are also technical, software methods that they can do to smooth out the load and manage power demand as well. And we've seen that in several events already where the root cause of oscillations and the solution was firmware updates or other types of software updates. So we also don't want to just limit ourselves to power grid solutions, but also can we look at other software-based solutions that can address a lot of these issues? So better scheduling of AI training jobs, better management of those load rampings, now that's something that really requires participation from load owners and developers there.
Yeah, I guess I'll just say for the mitigations of some of the issues, I just kind of used a cop-out answer. I just said study it. I think the next step, and this was somebody had asked in the chat, is, all right, what's the solution after you study? So I think when you take the study results and you find, okay, we lost voltage stability in the area when we operated the load like that, then you can kind of go back from an engineering design point of view and say, okay, well, can I change the way that my load works so that that won't happen? So I guess that's my what I would say for what's after study. Can I change the inputs to the study? And the main thing would be how can I change my load? You could also look at ways you can change the system so that the system doesn't lose stability. So I'll leave it there.
Yeah, thanks, Evan and Eric, for answering that question. I know we asked it twice, but in a different way, so to get some good answers from you. Yeah, I think this is a tricky question, and I think we've discussed about this when we were preparing for this seminar. And this also goes back to some of the questions that are being asked in the chat room as well. At the should large loads become a NERC registered entity? What would this mean if this is implemented to large load operators? And
Okay, I was at first really scared of this question, but I've been talking about it with a lot of people, and I've gotten a lot of really good ideas from folks. I think that if we have large loads that are posing severe risks to the BPS security, that could end up in registration if registration is determined to be able to mitigate those risks, right? But if other paths can be used to mitigate the risk, then registration wouldn't be necessary. So I think we've got to figure out, are there ways to mitigate this without registering? And if registering is the best way to de-risk, then perhaps that route will be taken. So I would encourage everybody to get involved in this conversation, from utilities to large loads, and figure out, are there ways to remedy these issues without registering? And if registering is the best path, what does that look like? So I think the best way we can get the answer to that question is by bringing everyone to the table.
And I'll just take I said in my presentation, large loads may need to become registered. Here in Texas, loads that are 75 megawatts and above have to go through an interconnection process. Now, a lot of that is submitted by their interconnecting transmission company. But the Texas legislature is also debating some Senate bills that would require load 75 and above to essentially register or at least provide more information to ERCOT and the Public Utility Commission where, for certain risks. So while register, is a fine line between registered them directly versus having them, they still have to submit data but not be registered. I think either way, we're going to see greater participation of the loads, and we're going to need to in order to make sure grid reliability in these processes, whether at NERC, at ERCOT, or with other grid operators and utilities. So you'll see a lot of you'll see some utilities that are implementing new interconnection forms and processes directly connecting with these large loads. So what level it may happen is still up for debate, but in some way, yes, these loads are going to have to be more active and participate more in the grid operations, essentially, and interconnection.
Yeah, thanks, Eric and Evan again. I think we are starting to hit time right now. We are almost at 12. With this, I'd just like to thank you, Eric and Evan, for all the time and knowledge that you're sharing with us today. I would also like to thank our attendees for their contributions and questions as well. Some of them were really thoughtful questions, but as in, like, this conversation is ongoing, and there's a lot that's going to happen in the space as well. Stay tuned for the next, as in IEEE, PESSYP, and CIGRE US NGN webinar. See you all soon.
Thank you, everybody, for joining today. Thank you, Evan, and thank you, Eric.
Thank you guys so much for the invite.
See you next time, Melvin. Bye.
Thanks.
Have a good
Bye.
day.